Hello, hello. We got Hubert, Adrian, and Ralph here. Welcome to the next and latest Live Data Pro session. Today we will go through streaming challenges, and I'm sure the experts here can have quite a few opinionated views around that topic. So let me share my screen now for a second. Let's see if I can get my presentation up and running. Okay, and let me get this into full mode view. Is that clear for everybody, the screen here?
I think so.
Oh, thank you.
It's coming. Here it is.
Yeah. It is? Okay, thanks, Ralph. Thanks for the confirmation. So while we go through these slides here, just a second, I'm going to start with the presentation of our speakers for today. We have a few of them, starting with Hubert, who is the O'Reilly author of Streaming Data Mesh and Streaming Databases, which is in early access. Hubert has 20 years of experience in big and fast data. He has experience consulting with financial, healthcare, telecommunication organizations, specifically around data. And then we have Ralph, who is the co-author of Streaming Databases. He's a lead enterprise Kafka engineer at Migros Genossenschaftsbund in Switzerland. I don't know if I pronounced that right, Ralph.
That's fine.
And before that, he was AI NLP researcher who has focused into solution architecture. He's received his PhD in computer science, NLP, in 2006. And before being part of Migros, he had spent 15 years at SAP, Bosch, Forecastly.
11.
Oh,
Okay,
11 years at SAP. Okay. I thought combined you
was
spent
combined.
SAP, Bosch, and Forecastly 15 years. There you go.
But doesn't matter.
And our very own Adrian, who has focused on Pathway. He's the head of product here at Pathway. He received his PhD in computer science at age 20. He founded a very popular online community for programming and developers called Spodge, and has co-authored more than 100 research publications. So anything else I missed, you guys can chip in, but I'm moving on.
Fine. I'm just impressed by PhD at 20. Mine was at 31.
That is definitely Adrian's talking point for sure.
I guess I was on less advanced topics than NLP at the time.
There we go. Okay, so with the presentation of our experts, we will set the stage with Hubert talking about streaming systems and how they fit in the current systems landscape. Go ahead, Hubert.
Great, thank you, Anup. I hope you can hear me.
Yes, we can.
So we're in the midst of writing this book, as Anup mentioned, that it is in early preview. This is a diagram in one of the chapters recently completed that kind of outlines the landscape in real-time analytics and databases today. If you look at these, the Venn diagram kind of helps you see what's happening in the ecosystem today. So on the top circles of the Venn diagram, do you have your operational plane and then your analytical plane. And if you look at those are data at rest data planes. At the bottom is your data movement or streaming data plane. And where these things overlap or where these emerging technologies are coming into light, right? Where you see these streaming OLTP database, then you have your HTAP databases that incorporate columnar and row-based ACID storage. But then the bottom, this is what enables them all to be basically real time, because it takes a lot of transformation to build these analytical views for real time consumption. and it gets complicated down there. And so this is a lot of this conversation is going to help unpack uh, what it is that we're trying to do with real time analytics, and and where, and depending on what your solution is and what you need, your use cases are, how or where to get started with real time analytics, right? And specifically, the left and the right hand side of the streaming plane. These are things that are not talked about a lot. We're going to talk about them here, what it means in real time analytics, and what you need to think about when you start to build real time solutions uh, for your use cases. Um, but so at the top, HTAP is your hybrid transactional and analytical plane databases. A lot of them are emerging, starting to think about real time streaming to enable real time transformations and building of analytical views. You're streaming OLTP databases on the left, and then you're streaming OLAP databases on the right. Not a lot of things, databases really fall on some of these overlapping sections, but you'll see that they are starting to incorporate some of these technologies in the build up. It's kind of migrate towards the middle there, NG meaning next generation real time databases.
And I
Okay.
think we'll talk about the NG side of it a little later too, Hubert. So
Yep.
thanks for setting the stage here, especially pointing out that split on that bottom half on the left side and the right side for the streaming data plane. Using this as our stage, I think we go straight into it's a kind of a deep dive already, but going from setting the stage to the three big problems you folks see, especially for the data team members who deliver value to the business with stream processing, usually the data scientists. There are three areas here, and I think Ralph is going to take the slide on. Ralph?
I can do that. So, I mean, first box is kind of clear. So that's the out of order and out of order data, late arriving data. So that's what we have in stream processing. That's one of the biggest challenges to get the settings right. I mean, all the stream processors around can cope with this, well, to more or less of an extent. But basically, you can do it, but it's very hard to configure and to do it right. It's also about time windows here. Get the time period right here. Watermarks in Kafka Streams or KSQL. There's other settings like a grace period and these kinds of things. Second thing is in the middle we have the problem for data scientists, especially to enable real-time training, so online machine learning and inference. That's still kind of an unsolved problem because the tool set, the ecosystem, especially around the streaming space, has traditionally been built out of the Java or JVM world, Java Scala, and there's so the Python support is coming. It's getting better, but it's not at the point where it's complete. And Pathway is one of the solutions which will help that. And the second thing is to get consistent results, because if you use stream processors, especially eventually consistent ones, we'll see that later, you can end up having like quite unexpected results, right? So that's not at least results which you don't expect in a typical data at rest, typical database, classical database setting.
Got it. Got it. And just around going to that second box here, the training and inference, is there a reason why are there unique challenges around the training side of it? Are there unique challenges around the inference side of it? Adrian, is that something you could speak about?
Yes, I guess in general, one of the thing that's challenging in streaming for data scientists in particular is that it's such a new area to data scientists, in that they most of the time they or we as data scientists approach a static data set, and the problem of like data arriving and real-time updates in general is both foreign from the point of view of tool set and of the approach we are taking. So I guess for each of these boxes, there's also the human element. It's a bit like, for example, if we take the middle box that you mentioned, enabling real-time training and inference. There's a certain question of model training, of understanding what model training is in real time, of moving away from a tool stack and approach where models are versioned or well controlled into one where models are changing all the time with a certain time constant. Let's say that there's a slight delay in the model changing, but still it's catching up as the data flows in. And this ability to adapt as data comes in is complicated by some of the other challenges mentioned on the slide. So, for example, if you have out of order or late arriving data, this starts to influence the logic in which you're working, because the late arriving data can influence the model with which you're working. And here, the data scientist is kind of faced with some completely new decisions, like, for example, how long should I wait for late data to arrive? What does it mean? Should I still include it in my model or not, etc.? So it's kind of a challenge which is on the boundary between technology and what can be handled and how it can be swept under the rug, and what the data scientist needs to actively think about to incorporate in their logic.
Got it. Got it. Now we'll have a whole different session around this, and I was telling this to Hubert a couple of days ago around these three areas, and I think each of them needs its own session and the challenges around it. Thanks for adding some color here, Adrian. Appreciate that. But today we will be focused on getting consistent results, and we'll be talking about consistency. So let's move on to that slide and let's understand what consistency means. Let's do a beginner level 101 on what is consistency and how does that relate to streaming. And maybe Hubert, you can talk about what the basics are and then go in deep into how that relates to streaming.
Right. I think the best way to really describe consistency is to go over the use case, and then and that'll define itself what consistency means, because it may mean different things to different personas that are trying to understand what we're talking about.
Got it.
We're speaking of consistency specifically in streaming, right?
Mm-hmm.
And results, when you ask the question and when you get emitted responses or results of an analytical query, what do you expect from that,
Got it.
right?
Should I go straight into that slide where you
Yeah,
have an example?
I would probably go to the next slide. So this is another excerpt in our book, and we use this use case called the toy bank, and this and it originally came from a blog that Jamie Brandon wrote, but I'll give you the summary here so you can kind of get the idea of how what we consider is consistent and how we test for it, right? So let's say there are three banks, and the use case is actually more banks, but here, just for simplicity, we have three banks, and we randomly choose an account to,
The accounts,
and
right?
yeah, there are three accounts.
In one
We
bank.
deprecate one, and we move that money to to another account randomly, right? So if everybody starts off with $0 in the account, we initiate transaction one, where we say, hey, account one, give account two $1. So it's immediately deprecated one by $1. Account one and account two is increased $1. But if you sum up all the accounts, you see it's still zero, right? If you continue this, again, account one is instructed to provide $1 to account three. So now it is -2, while account two and three are positive $1. Again, you sum those all together, that would be zero, right? And you continue that logic on until the very end. At any point, the sum should always be zero. So what does that mean? The sum should, if you were to put an alert on the sum, let's say if it's not zero, if it's greater than zero or less than zero, that could mean, especially with accounts of money, that could mean something significantly wrong with the transactions that are happening, right? At some point, somebody is no longer, the numbers don't add up, and there's money that's coming from somewhere that didn't really come from anywhere, but that's an alert, right? You don't want to be alerted if the sum hasn't changed, right? If the bottom row there hasn't changed, right? You only want to be alerted if it is not zero,
That is true.
right? So that's, to us, the way we test consistency in stream processing. Does that ever change? The sum of all these is counted. Does that ever change during the long running of these transactions?
Makes sense. Makes sense. That's a super easy explanation. Appreciate that. And I'll go to the next slide. I think you have more to add here.
Yeah.
Yeah,
So
so
this,
but
yeah.
go ahead.
Well, no, go ahead, Ralph. This is pretty self-explanatory.
Yeah, so basically, in order to set up this example, or also in the blog, we have a small Python program which basically sends messages to Kafka, where you model this toy bank example. So you always have an ID of this transaction, then you have an account where the money is coming from. So in the example, we have 10 accounts, not 3 in the real example. So here, in this case, there's basically $1. So the amount is 1. You can see it on the bottom. $1 is flowing from account 3 to account 0. So that's how the messages look like in the transactions topic. In the transactions topic, it's like just a one partition Kafka topic. So it's a very straightforward thing in this example. Yeah, and there's a timestamp, of course.
Yeah. So that's the event time, right?
Got it.
Yeah.
Right. So as opposed to processing time. So this is where the out of orderness starts to be a concern. What, when did I receive this transaction? Was it before or after something else? Does the math still add up to 0 if it's out of order, right? These are things you have to think about. A lot of times, in this use case, the transactions are commutative, right? That they can be out of order, but that it still adds up to 0. Does that make sense?
Got it. Makes sense. Yeah, does make sense. So
That's
TS here.
fascinating. Yeah, it's a very nice case in that there's only like one input to the system. There's one Kafka, and the information about the transaction is atomic. So, in terms of any problems with consistency, they're due to what's going on inside the streaming system itself. It's not the sources that are to blame, because the information came synchronized in this case. Yeah,
Right.
That's right. And talking of Kafka, I think the next slide is going to talk about that a little more. Is that right, Ralph?
Mm-hmm.
Okay. Let me just move on to the next slide.
Because in order to save you from the SQL statements, which would take a bit long to explain, I think, this is basically the data flow graph for the SQL setup, which models the example. So on the left-hand side, you see this one partition Kafka topic where the transactions are coming in. So the JSON, which we've seen before. And now kind of the crucial trick in this example, in a way, is that we tear these transactions apart, right? We create one view, which is for the credits, right? So where we basically include all the information where the money is coming to an account. And on the lower side, so we have these two boxes. I can't show my pointer, I think, but the low box is basically tearing. It's about the debits. So that's basically taking the information from the JSON where we say from account. So because the guy or the woman who is transferring the money to the other account is losing the money in a way.
Right.
That's the debits. And now the crucial point is in this example that we have an inner join where we join together these two views, which we have basically intentionally torn apart. So we've actually intentionally torn apart the transactions into two parts, and then we want to join them again. And that gives us the balance, right? The balance of the accounts, which you've seen at the beginning in this table. And there's just one more step where we sum up the total balance of all the accounts. So that's basically what should always give us this invariant of the sum 0, right? So the bank shouldn't lose money. It should just be 0 all the time because we set the starting value to be 0. Yeah, so that's how the SQL setup basically is, or it doesn't have to be SQL. It can be any kind of stream processing system. Mm-hmm.
Sounds good. And is there a reason why it was split into
Yeah.
these two?
I mean,
can you explain that a little more? Yeah,
I
especially
mean,
when the
because
transaction is a single transaction file.
Yeah, because that basically gives you this. We'll see that basically sets up a problem for eventually consistent stream processors. So for the classical stream processors like KSQL or Kafka Streams, Flink, and so on and so forth. Because for them, the problem is that they don't keep enough information in the background, so that they don't have enough bookkeeping.
Mm-hmm.
In the sense, just basically to save space, to save latency, to get better latency, and these kind of things. And we'll see in a minute what this can cause, because the inner join is the crucial part. So the join should still have the information that the transaction is one transaction, even though we've torn it apart into two views. And that's what's causing the problems now.
Right. So I think it's important to say that there's state included behind every one of these blue boxes.
Yeah.
Right. So this entire diagram is really a DAG or a graph of a flow of SQL statements that consume from one another and outputs to the very end, which is the total balance. And it's the states of these state stores between credits and debits. How are they joined together to create a balance or a view that is consistently 0?
Mm-hmm.
Right? And if they're not consistent, so you're setting up a test for the stream processor to make sure that it can understand the difference between when it joins to get these two credits and debit tables together, that the output is still 0.
Right. Which is based on the original example, Hubert, right? So that's almost everything here is going back to that screenshot you shared at the beginning. So keeping this in mind, let's talk about consistency in streaming.
Yeah.
So this is Ralph, you want to talk about this?
No, just go ahead.
Yeah. So this was a hard one to talk about a little bit. So let me set up the view really quickly. So the graph at the bottom is the x-axis is time. So from the left to the right, time is increasing. And on the y-axis, there's actually the 0 is in the middle of the graph. It's kind of hard to see. So anything so above it are positive numbers and below it are negative numbers, and that is the error, right? So we mentioned earlier that it had to be 0 at all times, the sum. So this is the sum of all accounts calculated by a stream processor. Okay. The stream processor, we are emitting values out of it to go into a Kafka topic. Okay, but in the meantime, we're also querying it inside of the stream processor as well. And at any moment, we want to know, is it not 0? And the stream processor is doing that work, that math, to see if it is 0. It isn't 0. And what you see here are the values coming out of the balance or the total, right? Yeah. It thinks that for a lot of this, it is not 0. It is not consistent. And at the end, what's happening is that you can see that there's this at least it's inconsistent as far as like the values. You can see there a trend there, right? That of inconsistency. But we have that. So the y-axis is the error. How far is it off from 0? Right.
Yeah. And I mean, what you can see here is that the last value, when we actually stop the stream, so in this example, it's 10,000 transactions, and then we stop the input stream, right? You can see that. I mean, you can't see it here, but you can see in the resulting topic that the last value, the very last one, is correct.
Hmm.
The very last one is
Right.
0, but you get all these intermediate values, which are not consistently 0. I mean, they're very far away, some of them. And the problem now is that in a productive use case, you can't stop the stream, right? In a productive use case, this and this is basically the problem which is caused here by eventual consistency, because this eventual point in time where it gets consistent is never happening in production, right?
Mm-hmm.
For this example, or would never happen in production for this example. So you would never be able to stop the stream. And if you can't stop the stream, you don't know which of these values is correct, because there's correct values. I mean, there's also correct values in between, but there's
Right.
also like hundreds of thousands of thousands of incorrect values. So and that gives you kind of a that's kind of the non-expected results, which, for example, someone who is just experienced with databases would get and would get frustrated, right, completely.
Right. In what use cases is it okay to, in this case, you mentioned that it's going to eventually get consistent. Is it okay to eventually wait for results? Like,
Yeah, I mean, the typical,
and what does that
yeah,
eventual wait mean for that end consumer or the end user, right? So, how do you
yeah.
explain that, Ralph?
So the point here is that classical stream processors are really built for windowed data in a way. So they're built for use cases where you have time windows of data, and then you do something with these finite windows of data, and the eventual here is the end of the time window, right?
Mm-hmm.
So basically, you always have an eventual point in time where you are at a point where you can calculate the final result, and then it's fine. So for all these use cases which are being which have been implemented at all these big tech companies like Netflix or Apple or whatever, um, these stream processing tools are mostly used for these use cases. But if you go more into use cases where you can't really establish windows, right, which are kind of more unbounded, like in this example, right, so then you run into problems if you don't really juggle around with times and all that stuff. And that's basically what makes stream processing hard for newbies to the stream processing field, which also I think also kind of stops a lot of people from actually just going into the stream processing space from the database space. So that
Got it.
basically narrows down the streaming market, in my view.
To some extent, we're talking here about very simple use cases because we're talking about databases, but in fact, the kind of database that we are looking at is really a kind of intelligent key value store. Like, let's say Redis, a cache that you ask for a value and you want to get this value and expect it to be correct. So this is, let's say, a system as to which people have certain expectations. It's a bit like if I'm using an API, I expect it to give back the correct result. I put a query, I expect the result. And the lack of this correct result is super counterintuitive. It's also a problem when working with computations of a certain depth, because the flow which has this inconsistency, which has this race condition in this case, ends up with a sum. And as I've said, if you wait till the end of, let's say, the data to flow, then this sum will after some time eventually become correct, and then you can again start pumping data in and again wait. But what if this sum is used in the course of further calculations, if you'd want to continue the
Yeah,
flow of data? And at
yeah,
that point, you'll be using the incorrect value of a sum.
That is true.
yeah,
That is
exactly.
true.
So if you basically if you compose, for example, SQL code of um, smaller scale, and then you compose them together, then this error basically explodes. So if you don't really watch it, and the thing is, I mean, what's happening if you just remember this data flow graph, this DAG from before, what's actually happening here? So why do we get these wrong results? Um, I think what's happening here is really like Adrian said, it's a race condition basically, because the join operators of these systems, they don't know what to join actually. So or basically they don't care. So they don't care about what to join. They just join whatever they get. And what can happen is that, for example, this credits view, or this operator which outputs the result of the credits is faster than the debits, right? And then what you do is you join parts of a newer transaction for credits with an older transaction from debits, and that's what basically gives you these ups and downs.
If you, Noop, if I could ask you just to step back one slide, it's actually a pretty nice visualization of race condition, because you can imagine that on the left hand side you have a first starting line, right, for the two, let's say, for the two cars, and then on the right hand side you have a finish line. But there are two lanes of the road, the upper lane and the lower lane, and one can overtake the other. So it's actually pretty intuitive with this graph to imagine why this kind of condition happens.
Yes.
Yeah. It's about the operators, and the inner join operator for classical stream processing systems doesn't care about what to join really. So it basically falls short of this condition, and you have to do. I mean, you can fix it. It's fixable. So we don't say that classical stream processors cannot do this, but you have to really think. So in this example, what you could do, you could take the event time, take it in the where condition, and join only if the event time or the ID of the transaction matches and so on.
Right.
But
and is that a traditional way of solving this? Is that the only way? Or is there another way in terms of, if you look at the window itself, you'd say, the business really doesn't need such a small window, and we could eventually get this answers. The business cannot respond to it. Is that, what are the typical ways of solving for this now?
I think
it's not about windows.
I think the next slide kind of covers this.
There you go.
Yeah.
So what we're doing here, what's in red there, are timestamps, right? You're trying to match up timestamps from the credits and debits. So basically, this could be rewritten as a temporal join, right? You could join by not just by the primary the key, the credit, the account key or account number, but you're also joining it at the timestamp or the moment when those two transactions, those two states were the same, right? So what you're doing is you're shifting the joins not just by account, but you're also aligning them up by timestamp. So you're doing a temporal join, right? So it's another. I like to think of stream processing as like working with data in 4 dimensions instead of 3 dimensions. So your fourth dimension is time. You always have to account for that, right? It's not just now. When you work with data at rest, it's always data right now. What does it look like now at this state? I can join it. You never have to think about time, right? Because it's always now. When you think of data that's moving, there's always a timestamp associated with it. And there's 2 different types of timestamps: event time, which is part of the payload when the event actually happened. Then there's the processing time when the stream processor received it. You got to choose one. Typically, is the event time, and that's where you want to tell the stream processor, hey, not just join by account, join by the timestamp at the time when it was. When you can join it, because there might not be a debit account that corresponds to a credit account at that same time, right? So
this solution, Hubert and Ralph, can it be universally applied into these kind of systems, or is that we have to be conscious about the join you do? In this case, you're doing a join on the timestamp. Is there something else, for example? I don't know. I mean, everything for me is time-based.
If you think, well, the problem is like so one problem is that in these classical systems, you do have to add stuff. So you have to basically bolt on consistency in a way as an afterthought if you want to do things like this. And also what can happen is you can fall into trapdoors easily. So there could be a trapdoor. For example, what could happen? You could have like 2 input streams, like 2 transaction input streams with different things which you would like to join later. And it could happen that these 2 streams give you, for example, two messages where the timestamp accidentally matches. So there's two different transactions, but they have the same timestamp. And then again, you get wrong results. And these can be errors which are very, very hard to find, maybe not at all. And only if like some customer complains or whatever. So that could be very hard to do. And also if you, the other choice would be to use the ID of the transaction to join, to use that in the where clause. But again, here you would have to have unique IDs if you scale this example a bit up, right? But imagine you don't have unique IDs in the input streams, then you would have to go to the data producers to change all that. This would take a lot of time. So it is fixable, but it also leads to or can lead to problems, and that's why it can be very costly. And
got it. And you mentioned the error side of it. And obviously there's a massive cost if you had to go and change the data producer side of it, right?
exactly.
But when if you go back to the example Adrian gave around this, what we call a running sum, would that problem also be solved with a join like this, or is that a continuous sum if I need to get that a running total? Adrian, what are your thoughts around that?
I guess the example that we used, which is really the minimum race course where two cars can kind of overtake, is such that this resolution might be sufficient. I think it's actually consistency is one of those places where you have to be very clear about your expectations. So as Hubert set the scene, we're talking here about the most classical version of consistency here. In fact, I would say that many developers, although they don't know about it, have an even higher expectation of consistency. So you got me thinking, in this system, if you put a Kafka at the input and a Kafka at the output, you could reasonably expect that the transactions are processed in the order in which they come in. Like a transaction comes in before, it's processed before. And in fact, whether this is the case, whether you actually get this with a running sum, does not follow either from the formulation of the SQL, even with this extra red safeguard, nor from the doing of the system. It may or may not follow from some promises of the state processor. So you may have things like being equal, but still transactions going in an order different than what was fed into them. All sorts of strange effects are possible. So it's sometimes I think it's super hard to say without taking the specific. Let's say we could take Flink specifically, we could take Kafka streams specifically, and look at the promises that they give, and see if it's resolved and to what extent it's resolved. And the problem being that it's hardly ever, only in a few cases, it's like a black box that you can safely say, hey, this is resolved, you don't have to worry about it.
Right. No, totally makes sense. And there's
basically you have to go from last word here. Sorry.
No, go ahead, Ralph.
Basically, that's the problem here is that you also, I mean, in a database world, you expect to be declarative, right? And so you write declarative, in this case, SQL, and you don't have to worry about these timing issues, race conditions and stuff. But if you go to stream processing right now in most systems, you have to think more. So you have to do the declarative work, and then you have to add on some, I don't know, imperative or whatever kind of work. So it's not completely declarative anymore. And that's also hard for data scientists to understand.
Right. And explain that a little more, because there was a question on imperative. How does that reflect? Because you have standard SQL, which you've shown here, Ralph, and what did that plus imperative look like?
The plus imperative, I mean, imperative is maybe not the right word, not completely, but it's you have to think about how is the flow going. So you have to think the entire flow from start to finish and how it is executed.
Right.
So you can't just write some declarative code and then you can be sure it works, but you have to do some additional thinking and maybe a lot of this. So that's the part here.
Exactly. And I think
It would probably be fair to say, maybe a bit controversial, that SQL executed by many eventually consistent stream processes is no longer declarative. It's a way of describing an imperative flow, and then you have to look at the internal system that's executing it, because the
Exactly.
outcomes may be different.
got it. Got it. And I'm going to switch into the mode of product marketing because I head up product marketing at Pathway. And this is the graph which can be better explained by Adrian on what does it mean? What does consistency mean in Pathway?
Yes, so a pathway, in this case, this illustration is pretty symptomatic. It shows that the error should be 0 in this case, and this is what you expect to happen. The error is 0 over time. So this is just a demonstration of like a simple form of consistency where you fed data in together and you expect the results to be processed together at a given time. More formally, any notion of consistency means you have to assume that data is coming in a certain order, in certain, you can think of it in certain transactions, which are either defined either by whoever is feeding them into the system, or they're defined informally by basically what the system took in. This forms a transaction, and with this in mind, the outputs of the system, or whatever can be retrieved by the system, corresponds to a valid transactional input state. So the understanding of what the system is doing doesn't require looking into the black box of the system. It just needs to understand how it's treating its inputs and what promises it gives on its outputs. So the promises on the outputs are basically that at any time the outputs that you can get from the system or that it's passing on to other systems correspond to some valid input state that the system has seen. The flow that we maintain here is a kind of prefix flow that, in addition to preserve like this validity, means that the system has correctly ingested a certain prefix of the data, prefix understood as data up to a certain time on each of its connectors, maybe not necessarily the same time for each connector, but up to some certain place. And the way everything that can be extracted from the system reflects such a valid input state. So you kind of at any time you are in a safe place.
Oh, perfect.
Yeah, so
That helps the Pathway side of it. And I know Hubert and Ralph had some commentary specifically around consistency. So
yeah,
use
I
that.
mean, it's basically, I mean, one thing to say is that eventually consistent stream processes have kind of a more leaky abstraction than the streaming engine, which is powering Pathway, which is differential data flow. So differential data flow actually has additional consistency built in, some kind of a form of snapshot isolation. So in databases, you also have snapshot isolation, and that's what's built into differential data flow as well, and that's powering Pathway. So that's, I think, what's happening.
That's absolutely the key to the story, I guess, and the kind of secret is to combine the engine as it processes data in a consistent way with the external understanding of consistency. And if a user together with a system enable this, it's possible to have like differential data flow maintaining, or a variant of differential data flow that's used by Pathway, maintaining internal consistency, and at the same time the external interface of the system being what users are used to in scaled deployments of Kafka, PubSub, other types of message queues. That is, outside there's an interface which is known as an upsert interface that you can update data, insert data. Externally, it behaves like this, while internally, the incrementality of the system is based on a different concept, which allows for data to be treated correctly without losing speed. I think this is also maybe one aspect to mention, because every asynchronous system, every problem that we are seeing here can be fixed by running an unscaled deployment on just a single thread, a single process which knows what it's doing. So if we were to collapse the whole data flow to just a single node, which is very simple, no threading, nothing like that, the problem would fix itself. Right? And the scaled counterpart of this is called like complete synchronization. If you slow down the work so that things wait for each other completely, then it's possible to get this effect. However, the real trick is not to do the slowdown. It's to be able to act somewhat asynchronously inside while maintaining consistency externally, and by maintaining how data relates to time. So data flowing through the system is not just data as understood as key value, but it's data understood as data in a certain point in time, and the time at which to which this data corresponds is known.
Right.
So I guess we had a question on.
Yeah, there's an out of order data question, and I was parking it because we wanted to talk about it in a separate webinar. But there's a question which popped up. We'll put that towards the end
We
before.
also have a question from Milind, and the question is about challenges in maintaining consistency while scaling stateful computations in the stream processing environment. And it's effectively, I don't know, I'd love to know, Hubert, Ralph, your perspective here, but I feel so much depends on which specific event stream processor we are talking about, because it's a very much system dependent question. And with Pathway, the answer is kind of simple, and I've given it. I mean, not much to worry about, but with others, I guess it very much depends.
Right. This is a hard topic, honestly. Consistency. A lot of times you may not need it, right? There's moments you may not you may need it significantly. Like, if think of this use case, right? You have a credit and you have a debit. I consider those, what, in a database or data warehousing world, fact data. These are actions being taken between objects and like the operational plane, right? You need consistency with that, okay? Because you need to align up, not just by ID but by time. If you're doing enrichment, right, and you only care about what the latest value is for an account, let's say you have a transaction coming in with debits and credits, and you just want to enrich them with a username or email and so on, and you only want the latest version of those dimensional data. You don't really, that doesn't, there's no consistency there you really need, right? So there are use cases for those, where you can just enrich the record, but if you want to do it in a way that you are controlling the timeline, right, you want to know when things actually occur at what moment, then you have to be more consistent. Like, you have to you leverage temporal joins, and ensure that you're thinking at that fourth dimensional way when you're building transformations in your
Right. And Hubert, just based
work.
on experience with financial institutions, you see more these kind of systems when you look at stream processing, especially with their strong audit trail needs. Um, do you see choices you can make in the stream processing layer based on what the capabilities are?
um like, yeah, you have choices are, you need to, if the more consistent you need to be, the closer you are to the operational plane, and the more requirement that you're going to be consistent, right?
Mm,
Because these are real-time decisions that people are making or viewing on their phone, those numbers better add up, right? So you need to be consistent there. If you're enriching at the end, you have like an end of day or end of hour even, reports, you could, you know tune the system to be eventually consistent. You could
right.
stop the stream for a minute, generate the report, regenerate, and have it catch up. And these are things that you could do. um uh, but a lot of these other use cases may not need that consistency. You're only just enriching, and a lot of times a lot of those don't even need much state at all,
Right.
right?
Makes sense. Makes sense. And now we are almost running out of time here, but I want to take it to the next slide here, um, and uh, wrap it up with the first setting the stage slide you set up for us, Hubert, and pointing out what you feel is next gen, and what that evolution looks like for people who are moving from the left side of your diagram to that NG section.
Right. So there is a trend I'm seeing of real time databases going towards the middle, right down there, right, and or not down there, like the middle of the Venn diagram. They might not completely get there, but you're still covering your true essence of what you're trying to solve, right? But providing a bit more so that you're closer to the next generation database. So what am I talking about? So in this diagram, you see that in the middle of the Venn diagram where everything is over, like you have both columnar and row based systems. You're able to do materialized views, or are able to asynchronously build tables for consumption at on the operational plane. So this diagram is really about real time analytics.
Mhm.
And data, I see databases going towards there, but I also see a more distributed approach where you don't want to basically separate, or you want to separate the idea of like a database and a stream processor, because um, you don't need that component, right? Like think of what a stream processor is. It's taking changes and it's emitting changes, right?
Mhm.
Um, so you're relinquishing the role of serving that data to other systems. That's what stream processing is, right? And if that's all you need, then that's all you should have. You don't need the other stuff, right? These overlaps are the other stuff where they want to converge things that to reduce infrastructure and to reduce complexity in their systems. If you have the things you need already, the stream processor, especially a very consistent one, is all you need to be able to build the real-time analytics.
Makes sense. Makes
But yeah,
sense.
so everything is converging to the middle there. Like HTAP doesn't have stream processing, but if you implement like a asynchronous materialized view or incremental view maintenance, you may start to migrate or move towards the streaming plane and cover more of the NG aspect. If you're a streaming OLTP database like a Materialize or a Rising Wave, you may want to incorporate. They may think about incorporating column or storage in their solution. If you are a streaming OLAP database like a Time Plus, you may want to start considering maybe um, uh, um, bringing in some row based, or bringing your data, at least a snapshot or reduced view of your analytics to the operational plane. How we should do that, right?
Right.
On the OLAP, you have lots of big data. You're talking to like data warehouses and object stores, right? All of that shouldn't go into the operational plan. There was a reason why we divided them to begin with, right?
Mhm.
But then that division has created overlaps between each other, really facilitated by real time streaming, um, to bring them together, right? I
Right.
hope that makes a little sense.
No, it makes a lot of sense. Thank you so much, Hubert and Ralph, for joining us today. And before we let the audience go, there's a great book which is coming up by Hubert and Ralph. It's planned when again? Q1 or Q2 of next year?
I say early Q2.
Early Q2 of next year. So look forward. The link will be posted on LinkedIn as we speak, which you can take
Yeah.
an early
Is,
preview.
is it the case, Hubert, with some of the chapters already accessible? That you can,
That's right. I think you can check chapter 5 is the plateau of the book, And then chapter 6 is where it gets really hairy. And we
Yes,
talk about consistency. And then chapter 7 is what you'll see this diagram in there in chapter
right.
7.
Not only just this diagram, there's a whole comparison of systems, streaming systems in the book. Well worth reading and understanding. The first 5 chapters, I believe, Hubert, were very basic, but you're building the stage for the next. You pointed out as hairy topics, so
Yeah.
highly recommended. Please feel free to get early access, and anytime you could reach out to myself, Adrian, to ask further questions around how our streaming systems work, and we'll wrap this up right now.
Good stuff.
Thank you so much.
Thank you.
Thanks.
Bye.
Thanks a lot. Bye.